Okay, so today is the review day for the second exam. You were supposed to have completed this thing and have it ready to turn in. Like I just said, we'll go over which ones you had questions, and you're allowed to change your answer and then turn it in after class, right? But you can't take it home and work on it tonight.
I'm gonna scan it in. Send it to you email.
I'll scan it in.
Okay.
You can just give it to me and I'll scan it and send it back to you. All right, so where do you want to start? Yep.
Last page.
We do parts 3 and 4.
Parts what?
3 and 4.
Okay. Question 3, and unfortunately this is not working today, so I cannot even project it on the screen, so you just have to have a paper copy.
The source is selected wrong.
Huh?
The source.
Well, they said it won't even turn
No,
on.
it's the media board itself is
Yeah.
not working.
So we're on the board today with paper to look at. Seems so old-fashioned, doesn't it? Back when I was a kid. So number 3 says, based on this plot, does there seem to be an interaction effect between gender and age group, or is it possible to tell? So the graph looks like I should have brought my reading glasses. You have 3 groups, under 21, 21 to 25, and 26 to 30, and you get a line that looks like this. I'm not using the same symbols, and then a line that's something like that, and then a line that's something like that, right? Okay, so the steepest one here is the 26 to 30 age group. The middle one is the middle age group. And the least steep is the under 21. Right? So then this is male and this is female. Okay? So, is there evidence of interaction?
Yes.
Yes.
The lines are not parallel.
Yes, the lines are not parallel. So number 3 is yes. And does there seem, I should have said why or why not, because I hate when I leave an answer and all you have to do is say yes.
It would be the difference here, and it would be the difference between the top and bottom.
What?
If you take a line and you drop it from male all the way up there, all the way down to the level of female over here, the main effect of gender would be.
Okay, that's problem number 4.
Okay.
Yeah, so hold that thought. So the reason that there's interaction, it's yes, since the lines have different slopes. And that's really all you need to say. And I forgot the word different. Have different slopes. Right? If they have the same slope, doesn't matter whether it's up, down, wherever, but if all the groups have roughly the same slope, doesn't ever be exactly the same, but as long as they're kind of similar, then you'd say, no, I don't really see interaction. But here there's very clear interaction. The difference between males and females for the older age is a really big difference. Think of horizontally, it's that much difference. But when I go to the underage, that difference is not very big. So there's a difference in the differences. That's interaction. Okay, then number 4, based on the plot, does there seem to be a main effect of gender? So that's what Jeremy was saying. If you look at the males, think of the average of those 3 points, and then the average of these 3 points for the females, that's a big difference. So there is evidence of a main effect of gender. If there was no main effect of gender, what would the plot look like?
You couldn't clearly see that male and female have different means.
Right. You couldn't clearly see that males and females have different means. So they wouldn't be sloped down, they would be roughly horizontal. right?
Or it would just be random, right? Like you would have just different lines.
Well, this is just a means plot, so so the randomness has been sort of taken out of it. But you're right. It could be some. One of them could slope up slightly, and one slope, whatever. But they would have about the same level. Then that'd be no main effect of gender. Yeah, Leanna.
I have it written in my notes that you can't really say anything about main effects when there's interaction.
That's true. It's hard to interpret main effect when there is interaction, right? Here it's still fairly possible because the males are certainly higher than the females are. It doesn't matter which group you're in, that is true. But if I say, what is the difference between males and females, I would have to say, well, it depends on what age group they're in. If they're in this 26 to 30, then there's a big difference. If they're in this one, then it's a small difference. Right? So you can't really, you definitely see evidence that there is a main effect, but describing that main effect to an audience, interpreting it to a readership or whatever would be difficult. Okay.
7. Oh, sorry, did we finish 4?
Yeah, I think I finished 4. So number 7, I noticed when I was making out the key to this, that number 5, that's left over from a previous semester. Did everybody understand number 5?
It's, yeah, it's Simpson's paradox.
That's right, it's Simpson's paradox. But we haven't talked about that in this class, because I just never even thought about Simpson's paradox. We did talk about it when we did the chi-square test, but I don't remember talking about it. But that's what that is. So then number 7, okay, so number 7 is just a one-way ANOVA, and we got to do contrast, right? So you have the different. It says a study was conducted to determine if piano lessons improve the spatial temporal reasoning of preschool children. So we have 78 children randomly selected, 34 were given piano lessons, 10 were given singing lessons, and so on. These groups were then compared on the change scores as post-treatment minus pre-treatment from a spatial reasoning test. So you can think of, in this case, they were interested in piano lessons. So that's the experimental treatment, and the other 3 groups are control groups. All right, so it's kind of unusual to have 3 control groups and 1 treatment group, or experimental group, but that's the case here.
So your groups, though, are all of those. For your I, big I is 4.
The big I is 4. This is a one-way ANOVA. There's one factor, and the factor is the type of lessons. And it has 4 levels. They got computer lessons, they got none lessons, so level 0, piano lessons, or singing lessons. Now they're ordered strangely in this output, but that's what SAS does to us. It alphabetizes. So it went C, computer, N, none, P for piano, and S for singing. And it ordered them that way, but that's fine. So what you're supposed to do is fill in the ANOVA table. So we have source, and then degrees of freedom, sum of squares, mean square, and F. And then we'll have a p-value for F. So they give us that the sum of squares for model is 207. 0.2814 if I go to 4 places. So this is model, and then error, and then total. So let's get degrees of freedom first. It's easiest to start with total degrees of freedom. It's always what? N minus 1. So what is the sample size?
78.
78, so that'll be 77. And then next easiest is model. And in a one-way ANOVA, what are the degrees of freedom for model? I minus 1. Capital I minus 1, and that would be 3. Right? So I equal number of levels of the factor. So that's a 4. So I minus 1 is a 3. And then the error you get by subtraction. Degrees of freedom have to add to the total degrees of freedom, so I need 74 error degrees of freedom. Okay? And then they tell us also that the total sum of squares is 760.7179. So how do I get the error sum of squares? By subtraction. Just like degrees of freedom, sums of squares have to add. So 760.7179 minus 207.28, and what do you get?
553.4365.
553.
Yeah.
Point what?
4365.
4365. Okay? So then to get mean squares,
Divide sum of square by degree of freedom.
divide sum of squares by degree of freedom. So 207 point whatever divided by 3 gives you
69.0938.
0938. Okay, 69.0938. And then 553.43 divided by 74.
7.4789.
7.4789. Alright?
You
Man,
divide
this is
those
easy.
to get that value of 9.2385.
Okay? So the F test statistic is the mean square for model divided by the mean square for error. So 69 divided by 7.5 is, what did you say?
9.2385.
9.2385.
Indeed. FCDF gives you less than 0.07.
So then the p-value, you're going to use FCDF function on your calculator from that number up to infinity. So 9.2385 up to a bunch of 9s. And then degrees of freedom, you have 2 degrees of freedom, 2 sets. Right? Model degrees of freedom in the numerator, error degrees of freedom in the denominator. So it's 3 and 74 degrees of freedom. And what did you say that gives you?
It's less than the 10,000, so.
Okay. So less than 0.0001.
Yeah, it's 4 zeros than 2 if you want to write it.
4 zeros and a 2, 0.0000 and a 2. SAS would put that less than 0.0001.
I guess because the reason I got confused on this is when you go to actually interpret, like in part B, state the null and alternative hypothesis for the ANOVA, that's saying that at least one of the means are different, but it doesn't tell you if the computer score is different.
Exactly.
So, are we, like, when we say the null, are we supposed to say that they're all the same, or are we supposed to say that? Because they want to test, I guess I'm confused if they want to test if piano lessons is different. So I don't know which null they're actually supposed to be testing, if that makes
Okay.
sense.
For this ANOVA, there's only one null. And what is that null?
That they're all the same.
That they're all the same. So mu, and I'm going to, instead of 1, 2, 3, 4, I'm going to put the first letter of each one, just to keep it straight. But in the book, they use the notation sub 1, sub 2, sub 3. That's fine. So the mean for computers is the same as the mean for, what's the next one? None?
Yeah, none, then piano, then singing.
Okay. All right, so there's your null hypothesis. They're all the same. So in English, we would say there's no differences. Then the alternative is what?
Then at least one.
of the
At
MJs.
At least one mu j is different. You can't say it's not zero because we're not saying they're equal to zero. In regression, we've added an equal zero out there, but here we don't. We don't expect the mean will be zero. We just expect they'll be the same. Is different than another, or different than the others, however you want to say it. Okay, then explain in words what the ANOVA is testing in this setting. What is the ANOVA testing?
The group means are the same.
Okay.
That each of the group means
That,
is the
that
same.
each of the group means is the same. In words, what this says. All the groups have the same mean. That it didn't matter what kind of lessons you got. It didn't change anything. So basically, getting lessons doesn't help. Okay? Report your conclusion from this hypothesis test. That's part C. Report the conclusion. Well, here's the p-value of that test. So what is the conclusion?
Reject them all.
Reject the null. It's a really small p-value. Remember what a p-value is. It's the probability you could get means that are this different. One of them is 0.45, one is 0.78, one is 0.6, one is 0.3. You could get means that are that different if there's really, in the population, no difference. It's almost impossible. Right? But since I did get means that were that different, then my null must not be true. So I'm going to reject it. Okay? Part D says approximately what percent of the variation in the scores can be attributed to the type of lessons they had. So part D, what do you use to talk about percent of variation? R squared. So does it give us R squared?
Yeah, 0.2724.
Yes, it does. Right. It's printed out. If you wanted to compute it yourself, you know how to do that, right? So if I blank that one out on Wednesday, you just take the sum of squares for model, divide by the sum of squares total. You get a number of 0.27248. So what percent? Then you would compute that as 0.25%, 27.25%. So it's not a lot of variability. It's statistically significant. But there's still, if you're explaining 27% of the variability, then you're not explaining 73% of the variability. A lot of other things that go into how they score on this test, not just what kind of lessons they got. Part E is the fun part. So let's see if I can squeeze it in over here. Part E says write out a contrast for comparing the piano group to the average of the other groups. Remember, a contrast is of the form Greek letter psi equal A1 mu1 plus A2 mu2 and so on. Like that. I used ones to be generic, 1 through 4. Here I was using C's and N's, but you could use the C's and N's and P's up here, and I will when I write it out for this problem. What has to be true of the coefficients? The A subs are the coefficients of the contrast. They're called the contrast coefficients. They have to add up to 0, right? So that you can test whether this thing is 0 or not. Okay? So for this problem, what will the contrast coefficients be?
1 and the rest -1/3.
Okay, you can use 1 and then the mean for the piano group. So we'll say, I'll put a 1, you wouldn't need to, but mean of the piano group, and then the others you said are
Negative 1/3.
negative 1/3. So negative 1/3 mu of computer minus 1/3 mu of none minus 1/3 mu of singing. Now, I wrote it out this way, but you could also write it as minus 1/3 times the sum. Right? That's algebraically equivalent, and this is how the book would write it out. Yes?
Do you do like 3 for the piano and then -1, -1, -1?
You sure could. You sure could. That's a great question. As long as the coefficients add up to 0, it's a contrast. And what you'll find is that the value you'll get back for the, remember we use a lowercase c for the sample estimate of that contrast. Your c will be 3 times what mine would be. But the p-value for the test will be identical. Because what will happen is the standard error of the contrast will have that extra 3 in it also, and so when you take the ratio to get your test statistic, it cancels out. Okay, so filling in numbers for C, the mean for the piano group, we're going to use the x bars, right? Not the mu's. We don't know the mu's, but we know the x bars. So I'm going to use the x bar for piano, which is 3.617. Actually 7.6 if I go to 4 places. Then minus 1/3 times, what do I do next? Computer, 0.45. Minus 1/3 times the none group, which is 0.7857. Minus 1/3, I'm running out of room here, so I'm going to cheat and use my eraser. Times the singing group. I didn't bring my reading glasses. That has a negative in front of it, doesn't it?
Yes.
Couldn't tell if it was a negative or a spot. Negative 0.3. So that one's actually going to have a negative times a negative. And I don't have the answers written down here. Can you tell me what this works out to be? $3.30574. Is that what you said?
Yeah.
Okay. Then Todd, yours would be 9.9 something something, right? 3 times that, which is just, that's fine too. Okay, so then compute the standard error of this estimate. So part F, standard error of C. What's the formula for standard error of a contrast?
The standard pole deviation, SP.
Okay, SP. And where do we get SP from our ANOVA table?
The root MSE.
It's the root MSE, which is actually given to you there. So I'll just write that under here. That's the root MSE times the square root of
The sum of the coefficients squared.
take each coefficient A, square it,
Divided by the sample size.
divide by the sample size. Right? So I'm not going to bother to write out all those numbers, but the coefficients are these numbers. 1, negative 1/3, negative 1/3, negative 1/3. So you're going to take each of those numbers and square them, divide by the sample size in that group, and those are given in the little table. So for the computer group, the sample size was 20. For the none group, it's 14. Piano group was 34, and singing it was 10. Right?
So it's the sum of the fraction, not the sum of the top.
Thank you. Yes. Since the n has a subscript of I on it, then it's got to be in the sum. If they were equal size groups, then you could factor it out, but you'd get the same answer. Okay, does anybody have a value for that standard error?
0.6399.
0.6399.
2. Yeah,
Anybody disagree with that?
3. Actually, it'd be 3.
635.
That'd be 993.
Yeah. Yeah, I used the actual.
If anybody didn't get quite that, but they got something close to that, I heard you saying you got 0.65 something?
0.635.
Oh,
Yeah.
635?
Because your root MSC that you give us is not the same if you were to take the root MSC
Yeah.
of the error.
Yeah, when SAS prints out the root MSE, it prints it out to what? 6 decimal places. But if you take the square root of this number, you're going to get something slightly different, right? It's just a matter of how many decimal places you keep in your intermediate calculations. On a test, you know, as long as I can tell you did the work correctly, I'm not going to penalize you for rounding different. Yeah.
So we're using the estimate, standard error to draw a conclusion. We're just going to look, see if it crosses 0 when we add and subtract.
Yes. Part G says write out null and alternative hypothesis for a test of this contrast. Do I ask you to do that test on the next page?
Yeah.
Okay. And what you're talking about, Corey, was adding and subtracting to get basically a confidence interval. That'll work also, but you would have to take this standard error times a t critical value to get margin of error, and then do the confidence interval. And then you'd be looking to see if that confidence interval contains 0 or not, because that's the hypothesized value. Right? And that's part G, write out the null and alternative hypothesis. So you can either do it as a hypothesis test, or you can do a confidence interval like that. So what's the null hypothesis?
Contrast equals 0.
The contrast equals 0. And you're using the Greek symbol, not the C. So if you wrote this, I'd go, eh. Right? You might get some partial credit. I don't have to do any fancy schmancy tests to see if C is 0, because I know what C is. It's 3.3. Hey, that's not 0. Right? But what I can't see is psi, the population value. C is hopefully a close estimate of that. So I base my test on C, but the test itself is whether the population value is 0. So the alternative is that it's not 0. And then how do I form a test statistic? And that would be part H on the next page.
Use the TCDF function.
What's that?
Use the TCDF.
You will, but before you use the TCDF, you got to first compute the T, right? And how do you compute the T test statistic?
Standard error divided by the contrast. Or
Okay,
contrast.
so the test statistic will be a T, and it will be the contrast minus its hypothesized value, which is 0, so you don't have to write it, over the standard error of the contrast, which is just 3.30574, divide by the 0.63992. And now, do you see, Todd, your standard error is 3 times bigger, right? And so the 3's will end up canceling. You get the same test statistic. And what is that value?
5.1658.
5.1658. Now, I don't really have to compute a p-value to know, ooh, that's really significant. How do I know that?
Because it's bigger than the 2.98 or whatever.
Because I got every t-table memorized.
Because for a t-table, that's pretty ridiculous.
Yeah, I mean, what is a test statistic? Except for that chi-square test, almost always a test statistic is number of standard errors. Your sample data is from your hypothesized value. That's 5 standard errors. That's way out in the tail. very small p-value.
1, 2.5
Is that what it is?
Wasn't like 6 sigma, 1 and 3.5 million?
Yeah, that's right, yeah, 16. So, to get the p-value though, this is a two-tailed test. So your TCDF function is only going to do one tail. So you got to use TCDF and then multiply by 2. So I'll just write it like this: 2 times TCDF function.
T stat.
What's that?
Put this T stat.
Yeah, with the T statistic value 5.1658, and I'm going to put it in absolute values because sometimes you get a negative test statistic, sometimes a positive. If it's a two-tailed test, just forget about the negative, take it off, and go from there up to infinity with then what degrees of freedom?
In -1.
No, degrees of freedom error, 74.
74 degrees of freedom. Right? So, air degrees of freedom. If you ever can't remember what the degrees of freedom are for a t-test based on an ANOVA or an ANCOVA or a regression or anything like that, just remember, oh, it's always the error degrees of freedom. And for our F statistic, the denominator degrees of freedom were the error degrees of freedom. So it's always the same. The t-tests that get done use the same error term, so same degrees of freedom. Okay? So what did you get for that p-value? Anybody get it out to?
0.0000195597.
I lost track. How many zeros?
5 zeros.
5 zeros and then what?
195597.
1955. So basically, it ain't happening.
If you could,
What's a p-value again?
the probability of collecting data like you did given the norm is true.
Right. So the null says that there's no difference between piano lessons and the average of the other three. There's no difference. The contrast is 0. Now, if that were true, what is the chance we could get a contrast value of 3.3?
It's not
That-
gonna happen.
0, almost. It's almost impossible. But we did, so the assumption of the null must be false. So we reject it.
And so what is the Bonferroni method? What does that have to do with this
Oh,
one?
I didn't do that, did I? Assume you have a total of 3 contrasts planned and use the Bonferroni method to adjust for the multiple comparisons. State the alpha level for the test. So this is still part of H. So I'll write Bon alpha, Bonferroni alpha is equal to what?
It's 0.05 divided by 3.
0.05 over 3, assuming you wanted to have a 0.05 overall level of significance, and almost always that's the number you use. So 0.05 would be
1/60th.
point, give me as a decimal, 0.05 divided by 3,
0.01666.
0.01676, 6 repeating.
So
Okay.
why are we dividing by 3?
Because that's how many comparisons were being made.
The comparison.
I mean, it's not stated, I haven't written that anywhere up here, but it says, assume you have a total of 3 contrasts planned. So you want to adjust for those 3. Then instead of comparing this p-value to 0.05, you have to compare it to 0.0166. But it's still hugely less. Is that a word? It's still a lot less than this. So you would still reject the null. The alternative to cutting your alpha by 3 is take your p-value and multiply it by 3, compare it to 0.05. It has the same effect. So that's called an adjusted p-value method of doing it instead of adjusting your alpha.
But we're still just testing though if piano lessons are different though, even though they say the 3 comparisons.
Yeah, they don't tell us what the other 2 are. But this contrast was testing piano lessons versus the average of the other 3. But I want to control for the fact that I got some other contrasts I want to do also. Yeah,
So
yeah.
then, when you say your conclusion, you would just say that piano lessons have a different, like, effect on their score than the other
Yes, yeah.
3 lessons?
You would say there is a difference in the mean score for children that got piano lessons compared to the average of the other 3 types of lessons. Yeah.
So the, when you modify the p-value, that's called the adjusted p-value. When you modify the alpha, it's called the adjusted alpha.
Right. So this is the Bonferroni adjusted alpha. If I take this p-value and multiply by 3, I get a Bonferroni adjusted p-value. It's all the same thing, just how you look at it.
Yeah, I completely lost track of the adjusted alpha. I thought that would be the answer.
That,
The adjusted alpha, the adjusted p-value.
yeah. Either way. Okay? I got 15 minutes left, so choose your
Last page.
questions.
Last page.
Choose. Okay,
Number
10.
E especially.
10 is the ANCOVA problem, right? So, it's completely coincidence, I think, that we still have 78 total for this one, but it's a different study. This one's 7th graders. The last one was elementary school, but they're just problems out of the textbook. I guess I'll erase the whole thing here. So data was collected on 78 7th grade students' GPA, and the GPAs are on a 10-point scale. Of interest is whether there's a difference between GPAs of males and females. An important covariate, however, is IQ, since higher IQs tend to be associated with higher GPAs. So below are the raw unadjusted means for GPA and IQ. Does it appear the unadjusted mean GPAs for females and males are different? So what you see is that females GPA, so I'm going to put G bar female. That's just my own cryptic notation. But G bar for females is 7.6965. GPA for males is 7.2816. Does it appear there's a difference? Well, you can't really just look at the means and decide if they're different or not. You have to look at the size of the variability around those means. So what are the standard deviations? 1.7 and 2.3. How much difference is there? About 0.4. So that's easily within the variability in this data. So I'd say it does not look to me like there's a significant difference. You could also make some argument based on GPA on a 10-point scale that, oh, a 7.7 isn't that different than a 7.3. Or you might say, well, that's a huge difference. That's the difference between getting into college or not, or whatever. Make an argument and it's fine. The point is these are unadjusted, so it's not accounting for IQ yet. And so your answer may change. But as a hint, if you look down below, it says output for one-way ANOVA unadjusted for IQ. What's the p-value there?
0.3966. So
0.3966. So
pretty
it's
likely. That's
so-
pretty good.
So a statistical test between the unadjusted means is not significant. So there's not a significant difference between males and females if you don't adjust for IQ. Then it says part, that was part B, right? Ignoring IQ, here's the ANOVA, blah, blah, blah. And then part C says, examine the following sets of SAS output. Determine if fitting an ANCOVA model is appropriate. So on the next page, there's a model 1 that has the ANCOVA adjusting for IQ, and then model 2 adds the interaction term. So what's the main thing you're looking for to decide if it's okay to fit an ANCOVA model?
Same slope.
Do they have equal slopes? And what's the test for equal slopes?
Is there interaction?
The interaction, that's right. So the interaction between gender and IQ. Because IQ is a continuous variable, so it's like in the regression setting. So if the slopes are different, that means you get a change in the slope when you go from one group to the other, and you model that using an interaction term, which is the product of the two, product of gender with IQ. So if you look at model number 2, look at the IQ star gender line at the bottom of the output, and you see what for the interaction? What's the p-value?
0.3432.
So what's the conclusion?
The slopes are the same.
If you be careful saying the slopes are the same,
Slope are equal.
there's not sufficient evidence to say they're different. They might not be exactly the same, but I don't have enough evidence to say they're different. So ANCOVA seems to be appropriate. So C, test for equal slopes by looking at the interaction of IQ and gender. Not significant. So not sufficient evidence to conclude slopes are different. I wrote but looking, and this should be by looking. Test for equal slopes by looking at the interaction of IQ and gender. Okay, then it says, part D, the p-value for the test for gender in the following ANCOVA is 0.0111. Okay, and that's in model 1. Since we've determined that interaction is not significant, then we would take it out and run the ANCOVA. Right? This is, you run that model first to say, is it okay to run ANCOVA? No interaction, so yeah, I can run ANCOVA. Now I run model 1, so I really sort of have those out of order. But.
So if there was interaction, you just end up separating two groups?
Well, yeah, if there is interaction, then technically analysis of covariance is not a valid thing to do. You could go ahead and base your analysis on that model 2 with the interaction term in there, but now we have a problem with interpreting the main effects. Is there a difference between genders? Well, I don't know. It depends on their IQ. Right? So if they have low IQ, I don't know. Maybe if they have high IQ, then maybe it's the other way around. You know, who knows? But it'd be really hard to interpret.
So are you saying ANCOVA is appropriate for model 1?
Yes. Okay, so we got the p-value for gender of 0.0111. Provide the conclusion of this test concerning gender.
Reject the null. If you conclude that the adjusted means for gender are significantly different.
Okay, reject the null. And that's never enough. You can't stop there. Right? If you stop there, it's -3. Tell me what that means in English.
The slopes or the GPA for male versus females are different, whatever, you know what I mean.
Okay, the mean GPA is different between males and females after or when, you can use whatever word, after controlling or adjusting for IQ. So this is an interesting example in that unadjusted, if you don't take IQ into account, it doesn't seem like there's any real difference between males and females' GPAs. But if you take IQ into account, now all of a sudden, ooh, there is a difference. Okay? Part E, compute the adjusted mean GPAs for each gender. Are they statistically significantly different? Compare this result to part A above. Okay, so E says to compute the adjusted means. Right? So I'm going to use my own cryptic notation just to keep things small, but I have GPA for females, and then I'm going to put adjusted. Right? Looks like I wrote fadge. Maybe put a hyphen in there. Right? So the adjusted mean GPA for females, that's what that means. Right? Is equal to, what's the formula for adjusted means? We did this right at the end of class on Friday. So
it's the weighted.
Corey, I know you know this.
It's the sample mean.
What?
The sample mean of the y variable.
Okay, it's the unadjusted mean, which I had written over there. The unadjusted mean, and then subtract off the adjustment.
The slope.
The slope, which is b sub 1, which is an estimate of beta sub 1. And sometimes I write that as a beta hat, sometimes as a b, depends on my mood, I guess. The book uses a b, I think. And then times, in parentheses,
Unadjusted mean of the x variable.
okay, now I need means of the x variable, right? These are the y variable, GPA. So now I need to adjust for IQ, so you know IQs are going to go in there, right? So you need the IQ score, so I'll say IQ bar for females minus the
Grand mean.
IQ bar grand mean. So I'll put a dot, right? Meaning I've averaged across that subscript, male, female. So in other words, if the female's IQ for this sample is less than the overall IQ in this sample, then I need to add something in. If this thing turns out to be negative, then I got a negative times a negative, I'm going to add something in. I'm going to increase their GPA mean a little bit because their IQs were lower, right? Which happens to be the case here. So let's fill in the numbers. The average GPA for females was 7.69, 76965. Now, where do I get that B1? That's the slope, right? For GPAs regressed on IQ scores. But it's in the SAS output.
Is it coefficient?
It's the parameter estimate, so the coefficient for IQ. Now the way, I don't have time to go through the whole thing, and it's not that important, but the way that you read the SAS output, if it's a categorical factor in an ANCOVA, then that's like the gender mean and for females and the gender mean for males. Those are mean values, but they're difference from the intercept. And then if it's a continuous covariate, then it's a slope. So it has both in that same output. Sometimes it's a mean value, mean difference. Sometimes it's a slope. So we want a slope, and it's 0.1079. 0.1079, and then the IQ means for females, going back to the table over here, in part A, it says the female IQ mean was 105.8387. Now I subtract off the grand mean, which is the table above that doesn't account for gender, and the overall IQ mean for all 78 observations is 108.9231. So whatever that works out to be, that's your adjusted mean. Does anybody have it worked out already?
8.0295.
8.0295, right? So unadjusted, females had a GPA of 7.69. But if you take into account IQ, that GPA actually goes up, 8.03. And it goes up because these 78 females have an IQ that's a little lower than the overall IQ. The males kick the females tiny on IQ in this particular sample of 7th graders. I suspect that's not the case in most classes. No offense to you guys. Alright, and then males will be the same exact thing. To do the males, what changes?
The Y.
Coefficient, but it's zero.
This would become G bar for males. This would become IQ bar for males. This number stays the same because we've assumed equal slopes. And then this number, that's the same. Okay, I'm out of time, so I can't do part F, but it says using the fitted model below, model 1, compute the predicted GPA for a female student with an IQ of 120. So you would have, you've got an intercept term, you've got an IQ parameter, right, a coefficient. So you're going to have that intercept, which is B0, plus B1 times their IQ, so for the ith person, and then plus whichever of the two terms is for females, and it's labeled for you. So plus the female value. I don't know how to write that here. It's like mu hat for females. That's parameter estimate, which is 0.96746. So that's going to be your predicted value. Since that's a very high IQ, 120, you'd expect this number to be above the mean for all females. So you better get a number that's above 8.03. Does anybody have what you do get?
You get 9.225216.
Okay, good. 9.22 rounds to 23.
Yeah.
Okay. All right, I'll let you go. Have a good time between now and Wednesday, and we'll see you then.